Okay, Assalamualaikum warahmatullahi wabarakatuh. First of all, I would like to welcome all of you to my class EET 426 Power Electronics 2, and in this lecture we will learn about isolated forward converter. Okay, first of all we will review the converter topologies. So in our case we will review the DC to DC converter topologies, and then we will look at the concept of DC transformer. Okay, because in this isolated converter, we will use a transformer. Usually transformer is used in AC circuit, but you know the DC to DC converter is DC circuit, so we want to use the transformer. So there are concepts called DC transformer, and we will look into that. After that, we will analyze the isolated buck converter or isolated forward converter. So both are the same. We will look at its advantages and disadvantages, and then we will cover the ideal and real transformer. We will review back the concept of ideal and real transformer, and we are interested to understand or investigate more about the leakage inductance. So this is the phenomena or the losses that occur in the transformer, and due to the leakage inductance there will be some overlap loss. So we will study about the overlap loss. Okay, here are the category of the DC to DC converter. The non-isolated converter is the one that you usually or you already covered during the previous lecture, which is the buck converter, the boost converter, buck boost converter, and then I believe you already covered the septic converter. And the one that we will cover after this is the isolated converter, in which we will cover the flyback converter, the forward converter, push-pull, and we will touch a little bit about the full bridge and half bridge converter. Here are the example of the non-isolated power converter, and like I said before, this is you already covered during the previous lecture. You cover the buck converter, buck boost converter, the boost converter, and the choke converter. Okay, this is the first isolated power converter that we are going to learn, and this is the forward converter. As you can see that the circuit itself is divided into two circuits. The first one is the input side, and you also have the output side, and the input and output is separated by this transformer here. Okay, the second isolated converter that we are going to learn in this course is the we call the flyback converter. So the structure is a little bit different, but it also have the input side and the output side, and then this separated by the coupled inductor here, and this is some sort of transformer we have here. Okay, the next one that we will learn is the push-pull converter. Okay, the same, but this time it have the two switch. Okay, remember the previous one, the forward and the flyback converter only have one switch, but for this converter they have two switches at the input side. Okay, the next one is the half bridge converter. This is also isolated converter. It have the input side and the output side, and for this one we have two switches like the push-pull converter, but we also have the capacitor here to divide the voltage, the input voltage, to two equal voltage here. So we have the equal amount of capacitance here, C1 and C2. And then the final one is the full bridge converter. It have the almost the same configuration with the half bridge, but for this one it have the 4 switches instead of 2. Okay, also have the input side and the output side, and it is separated by a transformer here. Okay, now we will look at the benefit of isolation. Why we want to have the isolation in the DC to DC circuit. The first one is of course the safety compliance. We want to prevent any damage that happen to the either side of the circuit, whether the input side or the output side, to affect the other side. Okay, let's say we have the faulty circuit in the input side, so it means that it will not give any effect to the output side in terms of damage. Okay, and then we want to isolate the high voltage and the low voltage circuit. Usually if you want to have the supply from the AC source, the from the TNB source, and then you will convert it to the from AC to DC using to the AC to DC circuit, and then you want to isolate that circuit so it will not affect the output side of the DC to DC converter. The second advantage is you can have you can break the ground loop. What you mean by ground loop is for the non-isolated DC to DC converter, mean that the ground is connected, okay, from the input to the output. So this can, I mean, if you have some noise occur at the input side, it will affect the other side. Okay, and the third one is you can have the floating outputs and level shifting. What you mean by floating output is because you disconnect the ground from the input side to the output side, mean that you can have the fixed voltage between the output terminal, but this voltage at the output terminal is not relative to the voltage at the input terminal. Okay, now we will look at the concept of the DC transformer. Okay, before we go to the DC transformer concept, this is the, I think you're familiar with this. This is the buck converter. Okay, now we have the input DC, the switch. Okay, we have the diode here, inductor and the capacitor. Okay, as you know that the basic converter have several limitations. It have the single input and single output, and then like we said, because the wiring or the connection, there is a direct connection between the input and output, so there is no isolation. Okay, and then like I mentioned before, this can cause some problem if the fault occur at the input side. It will affect the output side. Okay, and the output voltage relative to the input. Okay, when we have the, I mean, the non-isolated converter like this, the output voltage at this side is only dependent on the duty cycle. So when you adjust the duty cycle of this one, it will change the output voltage of this converter. Okay, for the this concept we will introduce the transformer. Okay, so after the switch here, we will introduce the transformer at this point. Okay, and this is how the DC transformer will look like. Okay, as you know that for the DC transformer, actually the transformer mainly only work with the AC. I mean, when you have the fluctuating current, so only then the transformer can work. If we just put the DC supply here, okay, the constant DC supply here, there will be no effect, or this transformer will not work, as the transformer work on the principle of the induction due to the change of the voltage and current at this side. So if you have the direct DC at this point, okay, the direct current at this point, there will be no fluctuating current, and the secondary side will not be, I mean, the power will not be induced at the secondary side. So to have, I mean, when you have the DC supply here, you need to have some sort of switch here, okay, when you on and off. When you on and off the switch here, it will make the I mean, the supply fluctuate. So that's why we can have the transformer working in the DC, I mean, the DC circuit here. Okay, so because, okay, the normal one, we have this switch, because here in the original isolated buck converter we already have the switch here, so we can remove this one. Okay, so this one will ensure, and another one, we have the diode here. We need this diode to ensure that the current will flow in one direction only. So for the DC transformer, the most important thing that you must have is the switch, and also the diode at the secondary side to ensure that the current flow in one direction. Okay, so but in our case here, because we want to put it in the isolated buck converter, so we can remove this switch, okay, because we already have the switch here. This is the basic transformer model that I believe all of you already familiar with. We have the I1 and V1, the input current and input voltage at the primary winding, and N1 is the number of turn at the primary winding. Then we have the output current and output voltage V2 and I2, and N2 is the number of turn at the secondary winding. And this, the equation here, the relation between the voltage, number of turn, and the current. Okay, and you have to know that this is for the ideal transformer, because we did not consider any losses to the circuit. Okay, so we have V1 over V2 equals to N1 over N2, and I1 over I2 equals to N2 over N1. The dot convention is a type of polarity marking for the transformer winding, and it can show, I mean, the relation between the primary and the secondary winding. In this example, we have the current flowing from this point, and the transformer here is marked with the dot at the upper side and the dot at the upper side at the secondary as well. Okay, so the dot can, I mean, let's say we want to change the dot at the secondary side. Okay, the dot refer to the, I mean, how you wind the transformer. Let's say for the primary one, you wind the transformer like this. Okay, sorry for the drawing. And at the secondary side also, you go for the same direction like this. Okay, so it means that it will have the same dot at the primary, okay, the dot, and the secondary we have the dot here. Okay, so if we want to change the dot, we will wind the secondary side with like this, the other direction, and then it will produce, the dot here will be sitting at the bottom. Okay, so that's how you change the dot notation, okay, by changing the way or the direction of your winding. Okay, for the dot convention, it means that when the voltage at the dotted terminal on one winding is positive, the voltage at the dotted terminal on the other winding is also positive. Okay, now we see the current is flowing like this. So at this side, this will be positive, okay, because the current is coming from this way. So the side here is positive. Okay, the dot side here is positive, and based on this convention, when the voltage at the dotted terminal on one winding is positive, okay, this one is positive, the voltage at the dotted terminal on the other winding is also positive, so this one must be positive as well. The second one, I mean actually it will mean the same thing. When the current enter the dotted terminal on the other winding, the current will leave the dotted terminal on the other winding. So the current is coming to the dotted end here, so and then it will leave the dotted terminal as well. So it come from here, the current will come from here, this is the direction, and at the secondary winding it will go out like this. It will go out from the dotted terminal. Okay, so what is so significant about the dotted winding here? Okay, let's say we have because the current is flowing this way, because the switch is on, we have the voltage here, and then the current will come from this way. Okay, so what will happen is, as we know, when current enter this side, this one will be positive, and due to the dot convention, we know that this side, the one with the dot, will be positive. So because this one is positive, we have the diode here. Okay, it means that the first diode here will be forward bias, because we have the positive voltage at the anode terminal. Okay, okay, winding polarity dot notation ensures D1 forward bias when the MOSFET is on. Okay, when MOSFET is on, this one will be positive and this one will be positive. Okay, because this one is positive, and then because this one positive, this one will be negative. This one will forward bias. Okay, forward bias. And then how about this one? This one, because at this terminal, this is the anode terminal, we have the negative voltage here, so this one will be reverse bias. Okay, so the current will not flow at this junction, because this is reverse bias. So we will have the forward transfer of energy from here. It can move to this side. Okay, if you compare this slide and the previous slide, at this point, what have changed is the switch has been moved from this side to this side. Okay, why we want to move the switch here? Okay, this is we are discussing about the way we construct the circuit. Originally, if you want to have the buck converter, the switch is here, and then you put the transformer. But the switch, uh, it is much better for the switch to move at this low side of the MOSFET, because at this point you will have the ground at this ground connected to this terminal of the MOSFET, so it is easier to on and off the transformer. Okay, that's why it's mentioned that easier drive requirement. What I mean by drive requirement is we have to put some voltage here at the transformer to make sure it's on and off. So it is much easier if we connect the one of the terminal of the MOSFET to the ground. Okay, so it's easier to make the MOSFET on and off. Okay, now we will look at one of the problem that can occur in this kind of circuit. As we know, this is the normal pass that we can give to the MOSFET to make it turn on. If we give this pass to MOSFET, it turn on, and this one it turn off. So the one complete cycle here is called the switching cycle. Okay, the problem is when we turn on the MOSFET, we give this signal, okay, and then the current flow here. This primary winding and the secondary winding will get charged. Okay, so there will be some induction occur to this secondary, and then due to the positive terminal here, this one will forward bias and the current can flow here. Okay, so this is the normal operation. But suddenly when you give this zero signal to the MOSFET, suddenly there will be the charge inside here, suddenly it will have no way to discharge. So this can cause a problem in terms of the core saturation. So what will happen is the core in the transformer will saturate, and this will result in increase in switching current the next time it turn on. Okay, so we must have another pathway that we have to create to ensure that the charge here still can flow, okay, or still can discharge during the switch turn off. Okay, so we must have one pathway that we must put into the circuit to ensure that this charge can be fully discharged during this time. Okay, so during the time it will be charged, and we must make sure during this time, during the switch turn off time, all the charge in the transformer can be discharged before it turn on again next cycle. Okay, in order to make all the charges inside of the transformer discharge during the switch off time, we must create this, the green one. This is called the demagnetization pathway. So it consists of another winding that we create, and the winding is the opposite, I mean the dot notation here, the way you wind the transformer is so that the polarity is, if this one is positive, this one will be positive at this side. Okay, so and you have to include reset diode here. Okay, we call it D reset, so the current can flow this way. Okay, now we will look at how the circuit work when we insert the demagnetization pathway. Okay, as you know, when the switch is on here, there will be a current flowing through here. As we know, when the current flow into the winding, at this point there will be positive terminal, and then at the dot side, at the secondary, there will be positive. So this diode will be forward bias. And how about this one? Okay, because this one at the dot terminal here is positive, this one it will be positive. So when this one positive at the cathode side, this diode, the D reset, will be reverse bias and no current can flow here. Okay, so the current flow like this in the primary circuit, and then at the secondary circuit the current will flow here. This one is off, and it will charge the inductor here, and charge the capacitor here, and also supply the load here. Okay, so this is what happened when the MOSFET is on. Okay, now what will happen, okay, and then the winding polarity dot notation will ensure that the reset forward bias when MOSFET is off, and D1 reverse bias when MOSFET is off. Okay, now we have the MOSFET off. We will see how the current flow here. Okay, when this one is off, as you know, I mean just now when it's on, the current flow like this. Okay, like this. So when this MOSFET is off, what will happen is the polarity of the primary inductor here, I mean the primary winding, will be reversed. So this one will become positive, okay, and at the dot point will be negative. So when this one is negative, at this point is also negative. Okay, when we have the negative here at the cathode side, so this diode will be forward bias and the current can flow from this side. Okay, so at the secondary side, because at the dot point is negative, here negative, this one will off, and this one, okay, this one positive, the diode here will be forward bias. Okay, so the flow of current now, all the charge in the transformer here, the primary side and the secondary side, there will be discharge. I mean all the power here will be induced in this circuit. Okay, and the current will flow like this. Okay, because now it have the one way to discharge. So this one will flow like this. Okay, and at the secondary side, okay, because the inductor is the current initially like this, when we remove the power from the circuit, okay, because this is off, what will happen is it will current will continue to flow this way. And for the capacitor, when the current enter, when we remove the power source, the current will go out from the way it come in. So the current initially come here. When we remove the power, it will go out from this side. So in the secondary circuit, the flow of current is like this, and also like this. Okay. Okay, now we move back to the circuit when the MOSFET is on. So when MOSFET is on, we want to know, in terms of the voltage and current relation. When MOSFET is on like this, as we know, the current will flow like this. Okay, now we have the VP. The VP is the voltage across the primary winding. The VP will be equals to E in. Okay, this is E in. Why the VP equals to E in? Because at this point it will be connected to this point, and because this is the circuit is closed, this point will be connected here. Okay, so the voltage across this one will be the same as the voltage across E in. Okay, now we will look at the VS. The VS is the voltage at the secondary side. So we will have the voltage here, the VP. Okay, because we have the relation of the transformer, we know that VS over VP will be equals to NS over NP. So when we move the VP to this side, so we become VS will be equals to NS over NP multiplied by VP. Okay, and because the VP is equal to E in, so we can also make it VS equals to NS over NP multiplied by E in. Okay, the next one is the VR. VR is the voltage, okay, across the reset winding. Okay, this is the reset winding. So the voltage here will be the negative of NR over NP multiplied by VP. Okay, the voltage will follow the ratio that we have. So but we have the negative because of this one. Okay, and then it also be the same as the negative NR over NP multiplied by E in. So this is the voltage across the VR here. And then we have the V switch. Okay, the voltage is equal to V switch on, and the VDR. VDR is here, the voltage here will be equals to negative E in plus VR. Negative E in plus VR. Okay, because we want to measure the voltage here, VDR here, so we will have to make the Kirchhoff voltage law here, and then when we solve the KVL, we will get the VDR will be equals to negative E in, okay, negative E in plus VR. So this is the voltage across the VDR. Okay, now we will look at the circuit when the MOSFET is off. Okay, and as you know, when the MOSFET is off, at this point we will have open circuit, and the current only can flow at this direction. Okay, and this one is forward bias, so you can consider short circuit here. So the terminal here, E in, is connected to the VR. So that's why when we want to find the VP, we have to use the relation between this NP and NR. Okay, because, and as you know, the dot notation is inverse here, the location. So we have the negative here. VP is equal to negative NP over NR multiplied by E in. Okay, so using the transformer relation, so we can find the voltage at VP. Okay, same for if you want to find the voltage at VS. This is equal to negative NS over NR multiplied by VR. Okay, and or this one is equal to NS over NR multiplied by E in, because in this circuit, because this one is connected to the VR, E in will be equals to VR. For VS, Okay, we have V switch, not VS, the V switch, the voltage across this switch terminal. You can see if you do the voltage, Kirchhoff voltage law around the bigger loop here, you will find that VS V switch is equal to E in plus VP, the E in here plus the voltage at this point. Okay, and if you replace the VP here with this equation, okay, NP over NR multiplied by E in, you will get the E in V switch is equal to E in multiplied by 1 plus NP over NR. Okay, and the VDR, okay, the voltage of the reset diode is equal to VDR when the switch is on. VDR on, we call it. Okay, in this slide, we want to show you the effect of the turn ratio and the duty cycle selection to the condition of the circuit, okay, whether it's good or not. Okay, so we know that during the MOSFET turn on, the VP, the voltage across the primary winding is equal to E in. So this is during the MOSFET on time, and during the MOSFET off time is equal to negative NP over NR multiplied by E in. So we know that during this time, this is the process of the magnetization of the winding. So when we supply the power to the winding, the winding will receive this amount of voltage, okay, the VP here. And then during the MOSFET turn off, okay, we know that the E in is already not connected directly to the E in is not connected directly to the primary winding. So the voltage that occur at the VP is equal to negative NP over NR multiplied by E in. So the VP will get the E in due to the NR. Okay, we have the winding at the NR that connect it to the relate it to the primary winding. So what will happen here is we have to make sure that the amount of the magnetization, we call it the magnetization potential here, during the switch turn on, when you turn off the switch, okay, you turn off the MOSFET, we have to make sure that the amount of energy we have here is the same as the amount of energy during the switch off time. Okay, so let's say if we at this particular point, okay, the this switch here, we charge it for the value less than 0.5. Okay, so for whatever value that we have, the NP over NR, okay, we know that we still have enough time to demagnetize the value, because to make it easy to understand, we have to give some value. Let's say for VP here is 100, okay, and then we give the duty cycle, let's say 0.4. Okay, imagine that VP is 100, the duty cycle is 0.4. So if we just multiply 100 multiplied by 0.4, we will get 40. So the amount of energy that we have to that we get in the primary is, let's say, 40. Okay, now at this during the switch off time, the value here, okay, let's say the NP here, NR is less than NP. Okay, we just give some random value. Let's say NP is 10 and NR is 5, half of the value. Okay, so what will happen is the value at the maximum here is NP over NR. So NP is 10, NR is 5. So here we have 2 multiplied by E in. E in here is E in, we give it 100 before this, right? So this one will be 200. The voltage here is 200. Okay, so because of that, we only need this particular time. Okay, we have 200, and then the energy that we need to discharge is around 40 only. At this point we only have 40, so here we have 200 here, so we have to calculate the amount of time. So let's say we have 200 multiplied by the duty cycle equals to 40. Okay, so the duty cycle I mean here is the amount of time from here to here. Okay, this is the duty cycle, this is the duty cycle to discharge during the switch off time, right? So what is the value of D? D is equal to, okay, 40 divided by 100, divided by 200. Okay, so you will get around 0.2. Okay, the duration of time you need here is 0.2. So you have enough time to discharge this energy. Okay, so the phase here will indicate whether it's good or not. Okay, for if it's mild here, I mean that it's good. Okay, but you have to know that the amount of duty cycle that is supposed to use, okay, the duty cycle that you must have to ensure that the circuit is operated in good condition is you have to use this formula. Okay, this formula will cover for all the case here. So if you just use this formula, okay, you have to ensure that your duty cycle must be less or equals to 1 over 1 plus nr over np. So if you meet this condition, that you can have a smiling phases here. Okay, this is the isolated converter advantages. I believe in the earlier stage of this chapter, we already cover the advantage of having the isolation, so this is just to the elaboration of it. Okay, the first advantage that we can have is possible to have multiple outputs because we use the transformer, and for transformer at the secondary side we can have multiple call it winding. So let's say we have one winding at the primary side and two windings at the secondary side, so we can have two outputs voltage. The second one is we don't have the common input output connection, so in terms of safety, if any fault occur at the input side, we can avoid any damage, significant damage to the secondary side or okay the output voltage side. And having we call it winding at the secondary winding of the transformer, we can change the output voltage polarity. Okay, because we can change the how we wind the secondary port, whether in clockwise or anti-clockwise direction, so it will affect our voltage polarity. Okay, and then finally, when we have the isolated converter advantage, when we have the transformer installed in the circuit, we can have another variable to control the output voltage. For the non-isolated converter like buck converter, boost converter, we can only change the output voltage by varying the turn ratio. I mean by varying the duty cycle. Okay, but having the transformer, we can change the magnitude of the output voltage by controlling the turns ratio. So the duty cycle is for let's say we can change from 0 to 1. For the turn ratio, we can play around with the N1, N2. Okay, in this converter circuit, we have one input voltage and two output voltages. Okay, and furthermore we have the output voltage of the first one and the second one is reverse in polarity. So how can we achieve this one? So to understand that, we have to understand how the current flow in this circuit as well as in the circuit. Okay, now we have the current, let's say the current flow this way. When the switch is turned on, the current will flow this way. So like I mentioned before, this one will be positive, this side will be positive. Okay, got due to the dot polarity here, we have this one positive, and this one will be positive. Okay, now we look at the first circuit. When we have this one positive, this is the anode of this diode, so this one will be short circuit, so the current can flow this way. Okay, and because we have negative here at the anode side here, so this one will be turned off or reverse bias. Okay, because the current can flow this way, so the direction of current is this way. Okay, it come to the capacitor and to the load. So because the current flow this way, this one will be positive and this one negative. Now we look at the second circuit. We have the positive here. It means that at this point is positive, this point will be negative. Okay, and then when we have negative at the this one anode, this is cathode, so when we have negative at the cathode side, this will allow a flow of current, so this will be forward bias. And how about this one? Because we have the positive at the cathode side, so this one will be turned off, so the current will flow this way, entering the capacitor and then entering the load, and will come out this way. Okay, so the current will go this way. So because we have the current coming from the bottom side here, we have positive voltage here and negative voltage here. So this is how you can have the different voltage polarity by changing the secondary winding. Okay, let's say this one you have the clockwise direction. For this one you will turn the other way, the anti-clockwise direction for the winding. Okay, previously we know the advantage of the isolated converter, but for everything in this world, when you have the advantage, you can also have some disadvantages. So for this case, when we have the isolated converter, when we have to include the transformer, that means we have to have some extra cost of the transformer, and then due to the size of the transformer, we must have extra size, and the transformer also is not, I mean, not light, so it's heavy. Okay, the big transformer can be very heavy, so you have extra cost, extra size, and extra weight. And because we have the transformer, inside the transformer we also have the winding resistance, so this occur another losses in the winding resistance, and we also have the core loss in the transformer. Okay, and due to the effect of the transformer also, we can have the leakage inductance. Okay, leakage inductance means that not all the flux from the primary circuit will go to the secondary, and this will occur some leakage inductance. So this will reduce the output voltage and as well as produce the transient voltage. This one, the final point, we already mentioned that because we have the transformer, it's possible that the core of the transformer will saturate, and to avoid saturation we need the core reset winding. Okay, in this part we will learn about the leakage inductance overlap and how it can affect the performance of the isolated forward converter. Okay, this is the circuit for ideal transformer. We have I primary, and then the voltage across the primary winding V primary. We have the number of turn of the primary winding NP, number of turn of the secondary winding NS. This is the output at the secondary winding V secondary, and then we have I secondary. Okay, the current going out from the secondary winding. And then this is the equation that we already familiar, Vp and S over Np equals to V secondary. Okay, and then for the uh, input voltage here, we have V primary, I primary is equal to V secondary, I secondary. So this is the conservation of power because we assume the ideal transformer. So the input power V multiplied by I will be equals to the output power V secondary multiplied by I secondary. So this one only occur when we have the efficiency of 100%. It means that we didn't consider any losses in this transformer. So that's why we consider ideal transformer. Okay, now we will look at the real transformer. In real transformer, the core itself, okay, the magnetic core have a finite permeability. So permeability is the ability to allow the flux to flow, okay, inside the core. For ideal transformer, this permeability is infinite. Okay, so in this real transformer, because we have the finite permeability, we require a magnetizing current Imag to establish the core flux. Okay, and then this effect is represented by the magnetizing current, magnetizing inductance Lm. So this one is Lm. Okay, Lm. And another parameter that we must have in real transformer is the core losses. Okay, because the core itself can conduct current and it can have the I square R losses. So this will be represented by RC here. Okay, by having these two component RC and Lm, we can introduce the losses occurred in the real. Another losses that we can have inside the real transformer is the winding copper losses. As you know, when we wind the core at the primary or at the secondary side, we have to wind using a copper wire. Okay, so the copper itself can introduce the I square R losses. So this will be represented, okay, by the primary and secondary winding resistance. So for primary circuit, it will be represented by Rp, okay, at the primary circuit, and for the secondary winding, it will be represented by Rs. So this is the I square R losses, or the losses due to the resistance of the wire inside the winding. Okay, in this part we will look at the leakage inductance parasitic element. So we will learn how this leakage inductance can occur in this forward converter circuit. Then we will look at how it affects the performance of the converter. Okay, the transformer leakage inductance can occur when we have imperfect magnetic linking between the windings, okay, between the primary and secondary winding. So imagine this is the what we call the core of the transformer. In ideal transformer, we will assume that all the flux that flow from the primary winding will go to the secondary winding. So this, I mean, we assume that there will be a perfect linking or linkage between the primary and secondary. But in actual, when we have the real transformer, we cannot achieve the perfect magnetic linking. So there are some flux that lost, I mean, didn't go to the secondary winding, or maybe go to the go through the air and come back to the primary winding. So this, we call it the imperfect magnetic linking between the windings. So this effect will be represented by the leakage inductance at the primary side, called LLP, and the leakage inductance at the secondary side is LLS. Okay, and the equation for the LP leak. Okay, so this is the size of the LP leak is equal to NP multiplied by the flux of the primary, the flux that leak, divided by IP. Okay, IP is the I primary. And then for the secondary one, the value of LS leakage, okay, this one, the LS leakage is equal to NS, the number of turn of the secondary winding, multiplied by the flux that have been leaked, divided by IS. Okay, in isolated converter, these two leakage inductance, which is the primary and secondary leakage inductance, will cause a negative effect. Okay, and the effect is it will reduce the output voltage, but the amount of the output voltage that will be reduced, to calculate this one, we need to know the value of the leakage inductance. Okay, this circuit show how to measure the leakage inductance in the transformer. So leakage inductance is an integral property of the transformer. So it means that when we have the open circuit test and we measure the using the LCR meter at the primary side, the reading that we have here is the L primary plus the leakage inductance at the primary side. Okay, to measure the leakage inductance, the LLP here, we will need to conduct the short circuit test. So we need to short the secondary side of the transformer, and when we measure the LCR using the LCR meter at the primary side, the reading that we will get is only the leakage inductance at this side. Okay, this is the isolated forward converter. When you take the consideration of the leakage inductance at the primary and the secondary side. Okay, and normally for isolated converter, the transformer itself, usually we will use the step down transformer. So we call it step down. Usually the VS, it's not usually, I mean for step down transformer, VS is lesser than VP and IS is bigger than the I primary. Okay, now we will look at how we can reflect or project the impedance from one side of the circuit, from primary to the secondary. Okay, let's say this is the impedance around here. We will call it the Z primary. This is the impedance, including the inductive or resistive component that we have here. And at the secondary side, this is the Z secondary, the impedance at the secondary. Okay, so if you have the we call the impedance of the secondary here, the equation is the Z primary will be equals to Z secondary multiplied by N primary over N secondary squared. Okay, so this is the equation to reflect one parameter of the transformer to the other one. Okay, so Z secondary multiplied by N primary over N secondary squared. So for the Z secondary, the equation is the other way around, Z primary multiplied by N secondary divided by N primary squared. Okay, now we have the L leakage primary and we want to project it to the secondary side. So what we have to do is we will use this equation. The L leak reflected, okay, I mean reflected to the secondary, is equal to LLP, the L from the primary, multiplied by NS over NP squared. So because we know that NS, okay, is much smaller, okay, for the step down transformer, because the NS is smaller than NP. So when this value you squared, let's say this is 2, this is 6. Okay, 1 1 2 3. So the what we call the constant here, we have 1 over 3 squared will be equals to 1 over 9. So this is 9 times smaller than the L leak. So in general, when we have the step down converter, when we reflect the value to the secondary side, the value will be much smaller than the original LP at this side. In the analysis of the leakage inductance, we don't want the value to be in the primary side. We want to transfer everything to the secondary side because we are interested to see the effect that we have at the secondary side, where the output we have the output at the secondary side. Okay, originally we will have the leakage inductance at the primary side, but we want to reflect the value to the secondary side, so we will replace it with the leakage inductance that have been reflected. Okay, in this slide I want to show the effect of the leakage inductance that we can have in this forward converter. So the effect is it will prevent the instantaneous commutation between the Schottky 1 here and Schottky 2. Okay, so let's say without the leakage inductance, the current of Schottky 1 will be 90 degree. It will turn when the switch is turned on. It will move to the next level of current. But due to the inductance, the characteristic of inductance is it will oppose the flow of current. So what will happen is the current will go like this. Okay, instead of directly reaching the second value, it will slowly reach the second level of current. So this is the effect of leakage inductance. So here the effect that it have for the Schottky 1 is, instead of when the VGS is turned on, instead of straight away reaching the second value, it will take time to reach this value. For the secondary current, not secondary current, for the I Schottky 2, before this, I mean when the switch is off, what will happen is it will have the flow of current here. So at this level, the blue line here. Okay, it's supposed to be when you reach this value, okay, when you reach the triggering point of VGS, we want the I Schottky 2 to be like this. But due to the leakage inductance that we have here, it will be like this. Okay, so this is the effect of the leakage inductance. Okay, so we have this phenomena when the transition from the VGS off to VGS on. Okay, and then another one we have at this point when okay, at this point when the transition between VGS on to VGS off. VGS is the voltage that we apply across the switch here. So we will have this effect at this point. Okay, at the transition when the VGS is off to VGS is on, and at this point. Okay, so during this time we will have two overlap. Okay, so this is one overlap and this is the second overlap between the Schottky 1 and Schottky 2 current. So when the Schottky 2 on, so when we have this Schottky 2 here, when we have this amount of current inside or through the Schottky 2, what it means that at that particular moment the VS2 is equal to 0. Okay, so this one, during this transition period, this voltage here is considered 0. Okay, because it's considered short circuit, the current still flow within or through the diode, so the voltage during that period is still 0. Okay, from previous slide, I believe I already explained why the 0 voltage here will affect the overall V out here. Okay, that is because we have the voltage drop at this point. Okay, due to the leakage inductance that we have. And then if we can see closely, okay, at this particular point, okay, this is the overlap interval number 2. Actually, there will be no effect, okay, to the overall output voltage, because during this time, okay, during this time, we know that the V secondary, okay, the V secondary already 0. So whatever happened at this point, it doesn't affect the uh, the output voltage that we have, okay, because the output voltage will be depend on the V secondary that occur around here. Okay, so during this time the V secondary already 0, so whatever happen or occurs to the VLR during this period, it doesn't matter. Okay, it will not affect the output voltage. But at this point we have the V secondary, but due to the leakage inductance, we have the Vs2 is not equal to the voltage V secondary. So this will introduce some voltage drop at the VLR, and this voltage drop at VLR will affect the output voltage, okay, during the switch on period. Okay, during the overlap, okay, we call this time is the overlap time here. The V secondary, okay, the V secondary will be equals to the VLR, okay, this the voltage across this one. Okay, during the overlap we know that this supposed to be some value, but because there are still current flowing to here, this one is 0. Okay, because the voltage here is 0, this point will be connected to this point. Okay, and then the voltage across here VLR will be equals to the voltage across the V secondary. Okay, and you know that the equation of the voltage of the inductor will be equals to the inductance itself multiplied by di over dt. Okay, and the di that we have here is the output current during that time, the output current divided by the overlap time, the duration of this, the t overlap. So during the overlap, this is the voltage V secondary that we will have. Okay, the T overlap, the one we have here. Okay, if we rearrange the equation, we will get the T overlap equals to the leakage inductance itself, okay, multiplied by I out, okay, divide by the V secondary. So if we have this equation and equals to this, right, V secondary equals to this. So if we rearrange this one, we move to here, V secondary move down, we will get this equation. So the effective duty cycle loss that we have in this circuit is equal to this. Delta D switch overlap is equal to the T overlap divided by the T switch, the overall timing. This is the T switch. Okay, and then if we replace the equation here, we have the LLR I out divided by V secondary. This is T overlap divided by T switch. So this T switch is, you can represent it by 1 minus F. So F you move on top of this. So this is the equation for the delta D switch overlap. Okay, and finally, I mean this one, we can replace the V secondary here is equal to the E in. So this is just equation of the that relate the primary and the secondary. E in multiplied by NS over NP. But in this case, yeah, we can include the VDS if we want to find the voltage drop across this switch during the on period. But usually we can ignore this. So the equation just become E in multiplied by NS over NP. Okay, now we will look at the voltage reduction that we have due to the leakage inductance effect. So the amount of voltage here during this period is delta V overlap equals to the leakage inductance multiplied by I out divided by T overlap. The I out is the current flowing through this point, and the T overlap is the duration at this point. Okay, but to understand the reduction, the overall reduction, we have to analyze it for the whole switching period. Okay, from here to here. So to get that particular information, this is the delta V out average will be equals to the voltage here, this voltage at this particular point, multiplied by the T overlap, the time at this point, divide by the overall switching period here. Okay, by having this value here, we can analyze it for the whole switching period. Okay, now if we replace this value, the delta V overlap, with this one, okay, we replace this to here, multiply by T overlap here. Okay, we will get, okay, you see we can cancel out this one, so we will left with LLR multiplied by I out and multiplied by F switch. Okay, here we have 1 over T switch will be equals to F switch. So you can see that the losses that occur here is the losses that is non-efficiency related V losses. So the losses that occur here is due to the we have the voltage is become 0 at this point. Okay, due to the effect of this one when both rectifier is on at the same time, we will have this effect or these losses during this period, and these losses is not related to the efficiency of the converter. Okay, so in summary, what we already covered in this lecture is we already reviewed the DC to DC converter topologies, and then we learn the analysis of the isolated forward converter, and then we already learn about the leakage inductance and the effect to the forward converter. So next in next lecture, I will show you the analysis or the calculation part for this isolated converter, how you can calculate the parameters, the losses that occur in the forward converter. So that's all for our lecture. I hope you can appreciate the content, and if you don't understand or want to ask about any part of the lecture, we can discuss it during our synchronous class, or you can text me the message and ask me personally. Okay, that's all. Assalamualaikum warahmatullahi wabarakatuh.